Okay, so in section 1, we learned how to evaluate limits graphically, right? By looking at the graphs. And I told you yesterday, or last time, that in math, there are always 3 ways to approach a problem. Graphically, which we did. Numerically, which we also did in section 1, right? That was when you plug in the numbers and you see what values they're approaching. And then the third way is analytically or algebraically. And that's what we're going to do today. So we're going to do limits algebraically. So let's first talk about properties of limits. Okay. The first thing we're going to look at is the limit as x approaches c of k, right? So for example, the limit as x approaches 2 of 3. So when you have something like this, whatever that is, that's your function. So in this case, this is y equals 3. Now, what does y equals 3 look like? If I were to graph y equals 3, it looks like this, correct? Okay, so when x is 0, what's y? Right, when x is 5, what's y? When x is negative 1,000, what's y? 3. So as x approaches c, what's y? 3, right? So here, when I have the limit as x approaches 2, this is x equals 2, and as I approach 2 from the left and the right, the y value is approaching 3. So the limit of this will just be 3. And that's the same if you have any constant. The limit of the function is just the constant value of k. All right? Now, what if you have the identity function? So take a look at this one here. The limit as x approaches c of x, right? This one here. So if you have that one, what's the function in this one that we're looking at? Y equals what? Y equals x, correct. And if your function is y equals x, and you graph it, right? This is y equals x. Well, what does that look like? As you're approaching any value, like 3, right? What's the y value going to approach? Also 3, right? Because whatever the x value is, the y value is the same, right? Because it's an identity function, x equals y. So here, the limit as x approaches 3 of x is just 3. So those are the basic ones. Everything else, any other polynomial function is basically a combination of those. All right? So let's take a look at some properties. Suppose you have 2 functions, f of x and g of x. All right? And as x approaches c, the limit of the first one is L, the limit of the second one is M. So if you add the functions, the limit of the sum is just L plus M. If you subtract the functions, the limit of that new function is L minus M. If you multiply them, product. If you multiply one function by a constant, the limit is going to get multiplied by the constant. Same with division, same with raising it to an exponent. Okay. So, what do I mean by this? I mean this. Suppose you have the limit as x approaches 3 of x plus 5. Okay? Now I have inside here 2 functions that I'm adding. Y equals x, y equals 5. So what I can do is I can look at these separately. The limit as x approaches 3 of x plus the limit as x approaches 3 of 5. And we just learned this. What's the limit for the first one? What's the limit? 3. And what about for the second one? 5. So that's just 8. Okay, that's how the properties are used. Now, do we have to do this every single time? Not really. I'll show you how these are all going to work. So, all right. So using properties of limits, evaluate the following. So what do you think the first one is? 3. How about the second one? The limit as x approaches root 2 of e. E. Right? Because e is just, right, a constant. Okay. Now, okay, so limits of polynomial functions. Okay. If you have a polynomial function, then the limit as x approaches c of that polynomial function is just p of c. What does that mean? To evaluate the limit, you just use direct substitution. Just plug in the limit into the function. Plug in the x value into the function. Rational functions. If you have a rational function, that's really two polynomial functions on top of each other. Again, you use direct substitution. So, take a look here. You want to find the limit as x approaches 2 of this function. We're just going to use direct substitution. Take this 2, plug it into the x's. So this will be 2 minus 3 over 2 times 2 squared minus 2 minus 15. This is negative 1 over negative 9, 1 over 9. You see how simple that is? Just plug in the function. Just plug in the number into the function. X equals negative 1. The limit as x approaches negative 1 of this. Negative 1 plus 3, root 2. That's it. Yep. Yep. What about this one? Negative 8 plus 6. Negative 2 in the root? DNE. Because the limit can never be an imaginary number. Because what is the limit? It's the value that the graph is approaching from the left and the right, and that can't be an imaginary number. So what happened here? Why is this DNE, if you think about it? If it's the square root of x plus 6, this is negative 6. That's how that looks, right? But now we're evaluating it at negative 8. There isn't even a graph there. The graph doesn't even exist over there, right? It's like barren country over there, right? So there's nothing there. So, okay. Here, the limit of this as x approaches a, well, same thing. Just plug the a into the x's. So 2a squared minus 5a plus 3. Yeah. It could be in, it could be in terms of a variable. It's okay. Numbers are overrated. Yeah. Yeah. So, indeterminate form. Now, as a certain someone said here, it's just too good to be true, right? So, and as we can see in C, right? There's all sorts of possibilities when you plug in a number into a function, right? You can get something that doesn't exist. You can also get things that might not necessarily give you direct information. We call that indeterminate form. When you do this direct substitution, and if you get 0 over 0, it's described as having indeterminate form because we don't know what 0 over 0 is, okay? We know that the limit as like 3 divided by a very small number is infinite, but 0 over 0, nope. That's not something that we can reason out, okay? Yeah.
Does that have to be 0 over 0, like 10 over 0?
No, 0 over 0 specifically. 10 over 0, we know exactly what that is. That's infinity. We talked about that before. Well, it's also infinitely large because it's the limit as the bottom approaches 0. So as the denominator gets very, very small, the whole fraction gets very, very big. Okay?
0?
Well, that's the thing is we don't ever plug in 0. It's always the limit as x approaches 0. It's always when that denominator is approaching 0.
Oh,
Okay, yeah. So it's indeterminate form because when you get 0 over 0, you don't know what is happening there. It's necessary to use other methods to determine the limits because it's possible that the limit exists or that it's negative or positive infinity. So when you get 0 over 0, you have to do some more algebra to simplify the function. And there are several things we can do. One of the things to get around it is factoring. So let's take a look at this. We plug in -2 into this, and then you get, like -8 minus blah, blah, blah over, you get 0 on top, 0 on the bottom when you plug in -2 here. So what we do is we say this equals to, okay, and we put like a little 0 over 0 here. That tells us I plugged in -2, I got 0. Now what I want to do is I want to simplify this function, and maybe I can get rid of some of the problem. What's giving me an issue here? It's that x plus 2 on the bottom, right? That's what's giving me an issue. So maybe I can get rid of it. So we have to now do some algebra on this problem. And as long as you're doing algebraic calculations on this problem, this is important, that limit symbol cannot go away. All right? So the next step here is I say this is the limit as x approaches -2 of, and let's factor this. So let me split it here. I'm going to factor by grouping x squared, x minus 3, minus 4, x minus 3, over x plus 2. Let's factor some more. This is the limit as x approaches -2, x squared minus 4, x minus 3. Okay, I'm starting to see something here. Let's factor some more. X plus 2, x minus 2, x minus 3, x plus 2. Now I can cancel the x plus 2's, correct? Okay, so this is equal to the limit as x approaches -2, x minus 2, x minus 3. Now that I got rid of the x plus 2, notice now when I plug in the -2, I no longer get 0 over 0. So now I plug in the -2, and I get, what do I get? -4 times -5, that's equal to +20. So that's the answer, +20. Now, let's pause and look at our notation. Hang on. Let's look at our notation. As long as I was doing algebraic calculations, that limit symbol stayed. And then the minute I plugged in the -2 into the function, that's when the limit symbol dropped. So it's incorrect for you to drop the limit symbol here, and it's incorrect for you to keep the limit symbol there. All right, that is like -1, like hands down. Okay, eyes closed. Ryan, when you plug in the 6 here, you get, so look, you get, 36 minus 42 plus 6, that's 0. And then here you get 3 times 36 minus 66 minus 42, that's also 0. Okay, so now we got 0 over 0. So I need to factor this. All right, so let's see. The limit as x approaches 6 of x minus 6, x minus 1. Here, what do I get? 3xx plus 7 minus 6. Okay? Oh, look, these go away. So I have the limit as x approaches 6, x minus 1 over 3x plus 7. Now I can plug in the 6. I get 6 minus 1 over 18 plus 7. 5 over 25. 1 over 5. Okay? All right. Next. Okay. All right, next. Take a look at this one. I plug in 25 into the numerator, I get 0. I plug in 25 into the denominator, and I get root 25, which is 5 minus 5, 0. So again, I get 0 over 0, right? Okay, well, that's not cool. But I can't factor this one. There's nothing to factor. Well, another way you can solve them, or you can simplify them, if you have a root in one of them, is a process called rationalizing. To rationalize this, you go to where the root is, and it doesn't matter if it's up in the denominator or up in the numerator or down in the denominator. This is root x minus 5. Its conjugate, do you guys remember? Yes, it's root x plus 5. So you have to multiply top and bottom by root x plus 5. And stay with me here, don't get ahead of me. So this is the limit as x approaches 25 of, in the numerator, I have x minus 25, root x plus 5. And I know you have the urge to just multiply that out, FOIL it. Don't resist that urge. Because in the bottom, what do you get? X minus 25. And what does that do? Cancels. Yes? So now I have the limit as x approaches 25, root x plus 5, that's just 10. Okay, well, let me write it out. So it's root 25 plus 5, 10. Okay? Yep.
So when we're doing this, we should always multiply at the bottom and leave the top. Like just
multiply where the root is, like where the conjugates are, and leave the other one. Because sometimes it'll be in the numerator and sometimes it'll be in the denominator. Okay? So multiply where the conjugates are, and then leave the one, you'll leave the other the same. Okay, take a look at this one. You plug in 0 into the root here. You get root 4, which is 2. 2 minus 2 is 0 over 0. Indeterminate, that's indeterminate. So, what's the conjugate here? 2 plus, yes. Yeah. Yeah. So,
I have a question.
Yeah.
What's the point of multiplying the top?
You have to, you're rationalizing, and you're rationalizing because you have a root. You have a root plus or minus something else. And you have to do wherever the root is, you have to multiply the conjugate by that. Top and bottom. Sometimes it'll be in the top, sometimes it'll be on the bottom. Okay, so this is the limit as x approaches 0 of, okay, the top is where I have the conjugates, right? So it has to be the square of the first term, 4, minus the square of the second term, x plus 4, over x times 2 plus root x plus 4. Okay? So, what's this going to look like now? When I distribute the negative, this is 4 minus x minus 4. Right? So, this is the limit as x approaches 0, negative x over x, 2 plus root x plus 4. Most common mistake is a student will forget about that negative, and that usually comes from not being organized enough, or your handwriting is messy, or something like that. So now look at what happens. One x cancels with another x. So I have the limit as x approaches 0, -1 over 2 plus root x plus 4. Look, my limit symbol is staying intact entirely, right? Until I need to plug in my number. Now I'm going to plug in the 0 so the limit drops. So this will be -1 over 2 plus root 0 plus 4, -1 over 4. Okay? Questions? Yes, no, no, yes. Okay. Now, so again, if you end up with a situation like this, right? Or let's say this is like 4 over x. If you ever end up with a situation like this, the limit as x approaches 0 of 4 over x, as the denominator goes to 0, this whole thing will be infinity. Okay? So, all right. So we'll talk more about that in a little bit. Okay, next. Okay. What if you have to find power functions at infinity? Look at how this looks. It's the limit as x approaches infinity of x to the n. Okay? Now, that will be infinity. But there is a situation here. As x approaches negative infinity, now we have a different situation. If you have the limit as x approaches negative infinity of x to the n, this depends on whether or not the n is odd or even. Okay? So for example, if you have the limit of x to the 4 as x approaches negative infinity, okay? If x is infinitely large, right? Let's say x is like -1,000,000. To the power of 4, that's positive infinity. Okay? But suppose you have the limit as x approaches negative infinity of x to the 5. Okay? Now suppose you have -1,000,000. To the power of 5, that's negative infinity. Is this making sense? Now, when you talk about polynomial functions, right? Take a look at this polynomial function here. You have 4x to the 6, 3x to the 5, and so on. We've done this before, right? If, let's say, x is 1,000,000,000. 1,000,000,000 to the 6, that's how many zeros? 9 times 6, that many zeros. 1,000,000,000 to the 5 is only 40 zeros. Okay? So 54, right? I'm sorry, 45 zeros. Okay? So it's quite different. So at infinity, we only ever look at the term with the highest exponent. The other ones, compared to that first exponent, are negligible, is what we call them. So because it's at infinity, you can ignore these and just take a look at that. And so as x approaches infinity, what would 4x to the 6 be? Positive infinity. Now, if I were to tell you, get on your spaceship and go to that location, positive infinity, would you know where to go? No, because it's undefined at, to a certain level, right? So whenever you have an infinity answer, we always do /dne. Okay? All right, here, which term are we going to look at? This one. As x approaches negative infinity, where is that going to go? Correct. It'll be infinity /dne because of the negative in front. Good. Okay, what about this one? Which one do we take? The last one. And it'll be negative infinity slash dne. What about the next one? Negative x squared.
But it's a negative, so it would be negative infinity.
Correct. Okay. All right. Okay. Let's do some of these. Okay, what about reciprocal functions? What if you have 1 over x? Okay. The limit as x approaches infinity of 1 over x. So if it's 1 over an infinitely large number, 0. If you have 1 pizza and you have to divide it over among an infinitely large group of people, how much is each going to get? 0. Okay? And the same if it's negative infinity, it'll be almost 0. Okay? So then how do we do rational functions? This is the same as how we did horizontal asymptotes, by the way. You guys remember how we do horizontal asymptotes? For rational functions, compare the degree of the numerator and the denominator. If the degree of the numerator is less than the denominator, the limit is 0. So take a look at this. Here. We're looking at the limit as x approaches infinity. Higher exponent on the bottom, just 0. Okay, you know what? I'm going to take a few more steps and show you why, just because I like you all. Okay? This is the limit as x approaches infinity of x squared over x cubed, which when you simplify is the limit as x approaches infinity of 1 over x, and that's just 0. Okay? Do you have to show me all that? No. You could just go straight to the 0. Okay? Please don't show me all that. You need to be quick on these things. Okay? You need to be quick. Yeah. Okay. If the degrees are equal, then you have to take the ratio of the leading coefficient. So, negative 2x cubed, positive 6x cubed, negative 2 over 6, negative a third. Okay. This is where it's different from the horizontal asymptote. If the numerator has a higher degree than the denominator, for the horizontal asymptote, we would just say no horizontal asymptote, remember? But here, what happens? So let's see. If it's x to the 5 over negative x cubed, this will reduce to negative x squared, right? Do you guys agree with me? Negative x squared. And if I look at that at infinity, what will that be? Positive or negative infinity? Negative infinity or dne. Okay? Because this will be the limit as x approaches infinity of negative x squared. Okay. We never, ever plug in infinity. You are never allowed to write that. Never are you allowed to write that. Don't do that. Don't do that. Infinity times 0? No. Infinity over infinity? No. 1 over infinity? No. Okay? Okay. All right, let's do this. What do you guys think? It's 0. It's 0 because it's 5 over x. 0. Oops. The next one? Well, circle, circle. What's the balance going to be here? Negative something x. Negative infinity slash dne. Because it's going to be like negative x, right? Negative 3/5 x is what's going to be left over when you simplify that.
What?
Am I going backwards?
What am I doing? We learned so many things.
Yes.
So it'll be the limit as x approaches infinity of negative 3/5 x. Now if x is infinitely large, Molly, if x is a billion, this will be negative 3/5 billion. So it's negative infinity.
But it's an odd.
Yeah, it's an odd. So without the negative, it would be positive infinity. But now you have a negative out front.
Wait, what is positive? You're just mixing them up. No, I'm not.
So when it's positive, it's just
Oh, I'm thinking when it's negative.
Negative,
Okay,
yeah.
I missed that.
yeah.
Okay.
So here, how about here?
7/2.
Correct. Okay, let's do piecewise functions very, very quickly because you guys are actually like very good at this. Okay, I can't tell you how important this is in calculus. I mean, it's just, I don't know. Everything in life is a piecewise function, so everything in calculus is a piecewise function. So, to evaluate limits of piecewise functions, you have to evaluate the left-hand and right-hand limits at each partition. If the left-hand limit is equal to the right-hand limit, then the limit exists. Okay, what do I mean by this? Here's what you do. You have to say, okay, so this is the limit as x approaches 3. You have to say, oh, you know what? I have a little bit of like notation mistake here. This should be f of x, and then we have to find the limit of f of x as x approaches 3. Okay, that's what we're finding. So here is what we're going to do. The limit of f of x, 3 from the minus side. The limit of f of x as x approaches 3 from the positive side. Okay? Now, this top portion here is x is less than or equal to 3. This is to the left of 3. So for the 3 from the minus side, I plug this 3 into here, and I get 13. For the other one, I plug this 3 into here, and I get 8. Are those two the same?
Yes.
Not today, they're not. Maybe yesterday they were. Today, they're not. Okay? So since they're not the same, therefore, that's therefore, right? Those 3 dots. The limit of f of x as x approaches 3, it does not exist. Okay? So here too, we're going to call this f of x, and we're going to say find the limit as x approaches negative 1 of f of x. So here's what we're going to do. Limit x approaches negative 1 of f of x from the minus side. Limit of f of x as x approaches minus 1 from the positive side. Okay. Plug in negative 1. Is 3. Plug in negative 1. It's 3. They're the same. So we say, therefore, the limit of f of x as x approaches negative 1 is 3. Okay? All right. So now you can do part 1 of the homework.